welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Aw, that's us. I'm Corinne Caputo. I'm a writer and a funny person, and I'm a friend to the universe and a friend to my co-host here.
Hi, that's me. I'm Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe. Mm-hmm. I miss the universe, but we are friendly enough that sometimes we have our spats. Yeah. We butt heads every once in a while.
Absolutely.
As all friendships do. And so today, I wanted to honor that part of our friendship with the universe by bringing us to the bumper cars at an amusement park.
I love the bumper cars.
I know. Probably not the best idea to record while we're in a bumper car, but Smart. I did sign us up. Don't you worry. We're going to have our session after our recording. For now, we just get to watch over everyone in the bumper car arena as they're driving and bumping into each other.
I love it.
But there's another reason I wanted to bring us to the bumper cars today, not just to represent our friendship to the universe, but also to represent what we're going to be talking about. This is perhaps a topic that not many people think about. Maybe people don't realize that this is something that is actively going on right now. But today we're going to be talking about galaxy mergers and collisions. Ooh. And just spoiler alert, listeners, galaxies are colliding, like right now, actively, as we speak, everywhere in the universe.
That is scary. But
is it scary?
Well, I think I'm afraid. Here's what happens. I always picture what if I was there? I will never be there, but what if I was there experiencing that? And I think I would feel fear.
Interesting. Corinne, what if I told you are almost experiencing it now?
Oh my God.
Yeah.
Uh-oh.
Does that not make you feel better?
Yes, I think it does. But
okay.
I'm like, what if I bump into something?
Yeah.
I don't even like bumping at the bumper cars. I just like driving.
You play avoid cars.
I'm here to drive around a loop.
Awesome. Honestly, same. So we can just do that together later on. But I think that by the end of this episode, you will learn that even when galaxies collide, the things in those galaxies really don't collide. So it's not as dangerous as people might expect. But we'll get into it. Let's talk about what happens. Yeah. Before we get to the what actually goes on during a galaxy collision, I want to kind of recap something that we would have talked about in a very early episode, I think episode 2 or 3.
Oh, wow.
Where we talked about different galaxy shapes and how astronomers classify galaxies.
That was an early episode.
Yeah, so early on, but you can go back and listen to that episode, or here is the recap. So Edwin Hubble in the 1920s, he realized for the first time that the Milky Way is a galaxy and that there are a bunch of other galaxies like it in the universe. And once he realized that there are these things called galaxies, of course, he decided he needed to classify them and put them into categories. And he decided to classify them according to their shape. And he arranged them in this nice order. He divided them into different groups. And that scheme, that classification scheme that he came up with, astronomers call it the Hubble tuning fork. We can put images maybe on our Instagram. But it does look like a tuning fork. There's a straight line, and then it branches off into 2 lines going from left to right. So he noticed that, broadly speaking, there are 2 different shapes of galaxies. On the left of his tuning fork, he had the elliptical galaxies, which he called early types. And then on the right side of the tuning fork, he had spiral galaxies, like the Milky Way, and he called those late types. I think I've actually said it on the pod before, and I apologize, but it is a really common misconception that when Hubble made this classification scheme, he genuinely thought that elliptical galaxies or early type galaxies evolved into late type spiral galaxies. But that is not the case. He didn't think that it evolved in that way. He actually said that it was just based on their position in the graph. Like, when he said early type, he just meant the stuff on the left side, and late type just means the stuff on the right side.
I don't know. That sounds like you're covering your tracks. You're like, oh,
right?
No.
Right? I agree with you. He wrote in his paper where he was talking about his classification scheme, quote, temporal connotations are made at one's own peril. So he did write in that it's not saying anything about time evolution.
Yeah.
But it's still a little shady. Like, why? There might have been some inspiration from old astronomy nomenclature for stars, where early stars are hot and bright stars, like the O, B, and A types, and a late type star is cold, like the M and K stars. And I guess that could have been because ellipticals, even though they are often older than spiral galaxies, and they often have older, cooler stars in them, elliptical galaxies have a lot of really hot gas. So I guess elliptical galaxies could have higher temperatures on average than spiral galaxies, and maybe that's why Hubble called them early types, because they were hot.
Yeah.
Oh well. Whatever his reasoning was, the opposite is actually true. Spiral galaxies are usually younger. They usually have young, hot stars that are newly formed. And over time, those spiral galaxies merge, and the result is often an elliptical galaxy. And those elliptical galaxies are older. They have older populations of stars, so they're cooler and a little bit dimmer. When astronomers have looked out at the universe and kind of like counted the different galaxies they see, about 20% of the galaxies that we know about are elliptical galaxies, and about 60% are spirals. So spirals are by far the most common galaxy shape. And then the remaining 20%, those are irregular galaxies or something called lenticular galaxies. And on Hubble's tuning fork, lenticular galaxies sit right in the middle between elliptical and spiral galaxies. But really, that extra 20% is like irregular blobs.
Oh, okay.
And it's really the spiral galaxies have the most structure, and then elliptical galaxies have some structure, but it's more chaotic because they were made when two spirals smushed together.
So is irregular like a catch-all term for anything?
Blobby?
Yeah.
Yeah. We have probably like 5% of the galaxies are just called irregular, which means their shape can't be neatly confined into
can't label it.
a box. Yeah. I relate.
Yeah.
Corinne, how many galaxies right now are actively merging, do you think?
Oh my
Like
gosh.
what percentage would you guess?
I'm going to say like 25%.
Damn it, Corinne.
Is that right?
Yes.
Okay, because that was a real out of nowhere guess. That was like,
You
I'm just
say
going to
that
go
every
a quarter.
time.
I know. I'm channeling someone. I don't know who yet, but I'm asking the gods to give me these answers, and they come in.
Yeah. You're
that one
channeling
really
our good
shocked
buddy,
me.
the universe.
Yes. Oh, my friend.
It shocked you?
That guess being right shocked me because I really was just saying a number.
Yeah. To be fair, we don't have a super precise value for this.
Oh, okay, perfect.
Astronomers estimate that between 10 and 25% of galaxies are actively merging, and that number is higher for galaxies that are near the centers of their galaxy clusters, just because there are a lot of galaxies around them for them to merge with. So young, hot galaxies like spirals experience more mergers, and the galaxies in the centers of clusters, we call them central cluster galaxies. They experience more mergers. On average, it takes about 2 billion years for the whole merger process from beginning to end to happen. So from like first contact to, hey, we're a new elliptical galaxy now, takes on average 2 billion years. It can be shorter than that. It can also be much longer than that. I've read estimates for the Milky Way Andromeda merger that's going to happen, taking up to 6 billion years to complete.
Long time.
A very long time. And that's because when these galaxy mergers happen, the galaxies don't just like smush together and stick with each other.
Yeah.
They might pass by each other and like interact a little bit, but they'll really miss each other. They'll move like, millions of light years away from each other, and then they'll come back together and they'll do that dance a bunch of times, getting closer and closer until it is one big elliptical galaxy with their stuff mixed all together. Broadly speaking, mergers can be minor or major. And that just depends on the mass ratios of the galaxies involved. So if one galaxy in the merger is a lot bigger than the other, like more than 3 times the mass or size, then that is considered a minor merger because you have a big galaxy and a little galaxy coming together. Major mergers are when the galaxies are closer in size, where the ratio is less than 3 to 1. And they're called major mergers because there's more mass, there's more energy involved, and so they actually are like more energetic interactions. But all of these mergers, minor or major, are crucial to galaxy evolution. That's how galaxies grow. That's how galaxies get new gas to produce new stars. Although sometimes galaxy mergers can quench star formation in some ways by flinging a bunch of material out. So it really is like a complicated process.
Yeah.
And let's just get into it. Like what actually happens when galaxies merge? Well, your biggest concern, it seems, was things touching, like stars in those galaxies touching. Okay. It is a classic exercise for young astronomy students to try and estimate how many individual stars will collide when the Milky Way and Andromeda galaxies collide. You can do this the easy way, and there are like increasingly complicated ways that you can do it by just like adding in more factors. But the simple way just depends on like the stellar number density in a given region, like how close together or how far apart are stars on average. But if you want to get more complicated or more precise, then you also have to take into account the sizes of the stars and the like how fast the galaxies are moving towards each other and the angle that they're approaching each other from. But even if you add in all of that extra information, the answer doesn't really change. The answer is always going to be basically 0. Even though both of these galaxies have on the order of 1 trillion stars in them, because space is so spread apart, the stars aren't going to touch.
That's a relief.
It's a relief, yeah. Just to give you like a point of comparison, the distance between stars is more than 1,000 times the size of those stars.
Oh, wow. That's so much space. There is so much space.
There's so much space. Yeah. And so no matter how fast the galaxies are moving or how they approach each other, because there's so much space, the stars are just going to pass right by each other.
Wow.
Yeah. So hopefully that assuages your concern.
It does. It does.
Score. Other things are going to happen. Star formation. I remember hearing when I was coming up as a young astronomy student that when galaxies collide, new stars form. And that is very true, because when the galaxies collide, their gas also mixes with each other. And when you have gas moving around, it is more likely to produce new stars. But in doing research for this episode, I dug into more recent studies and got further into the details, and I learned that star formation doesn't increase as much as I expected. I think maybe that's because when the galaxies merge, yes, the gas is mixing, but there are more stars around and it's a more energetic environment, so I think that gas is hotter than it should be to produce stars. Because if you remember from one of our star episodes, in order for a star to form, the gas cloud needs to cool down and contract. And if the gas is too warm, then it's not going to be able to contract. So star formation, it doesn't increase as much as I thought it would. And it's not even as simple as that. It also depends on whether it's a major or a minor merger. I found this study by Pearson et al. From 2019 in the journal Astronomy and Astrophysics. And they used neural networks, so some type of machine learning, which is a kind of basic artificial intelligence. They use these neural networks to identify a bunch of different galaxy mergers in a handful of different surveys. And the neural network is better at identifying those mergers than we are just by eye, because it can find information that our eyes can't see.
Sure.
And what they concluded is that the star formation rate for galaxies that are merging is within a factor of 1.2 of the star formation rate of non-merging galaxies. So it really doesn't increase it by that much, maybe 20%, if that. And there was a paper by Davies et al. In 2015 that saw some differences from minor versus major mergers. It seems like no matter what, the bigger galaxy in the interaction sees an increase in star formation rate, probably because the bigger galaxy, having more mass, is better able to absorb the gas and the material from the smaller galaxy just through its gravitational influence.
Oh, okay.
So the bigger galaxy, it always gets a burst of star formation. But the smaller galaxy, what happens there kind of depends on what kind of merger it is. In a major merger, where the two galaxies are closer together in size, the less massive galaxy sees a short period of new star formation just after the merger. So in a major merger, both of the galaxies see a little uptick in star formation. In a minor merger, though, the less massive galaxy actually sees a suppression in star formation. So the star formation rate goes down for small galaxies in minor mergers, which means in a minor merger, that bigger galaxy is just really being a bully and stealing all of the gas from the smaller galaxy.
That was
which I
like
love.
Me in the womb. I was a lot bigger than my brother.
Interesting. Is he now bigger than you?
Oh, 100%.
Oh, okay.
Yeah.
Damn.
No, it didn't stick.
But it was nice while it lasted, I'm sure.
I was on top.
Black holes also get to combine when their galaxies combine, and we think that this might be how the supermassive black holes form, because it's hard to figure out how you could get a really, really massive black hole to form just from the collapse of a star, which is how the lighter black holes form. We have seen evidence of two black holes merging, but only through gravitational waves and not through light. So we have never actually seen what it looks like when two black holes merge. But we have a few candidates for systems that might let us see it in the future. I found a bunch of different articles talking about one system of colliding galaxies that's special because both of these galaxies have quasars in them. So I can't remember if we talked about this in our black hole episode. We probably did. But a quasar is just a very energetic black hole that has so much energy, it actually shoots out these jets of light-emitting particles. So you see these two streams of light coming out of the black hole. And because both of the black holes in these galaxies have these streams of light, we can see them. We can see how they're moving instead of just detecting the gravitational waves eventually. So I think they're still pretty far apart from each other.
Yeah.
But by finding this system, we can be better at looking for other systems that are like it, but the black holes are closer together.
Sure.
So maybe with systems like this, we will be able to see a black hole merger.
Fun.
It'll be fun.
I am curious what it looks like, but I am wary.
Yes. Yes. As we should be. A black hole merger is probably the most energetic event in the universe that we could capture. They are so energetic that they produce like the very heavy elements in on the periodic table, like platinum. But yeah, they are very energetic. That's why they give off strong enough gravitational waves that our dinky little instruments can actually detect.
Sure.
But these things happen so far away. Like these two black holes are in galaxies in in a different neighborhood of the universe. We're so far away.
Love it.
Yeah.
Stay over there.
It's not just things coming together that happens when galaxies collide. Stuff also gets flung out of the system. So stars, along with their planets, perhaps, also gas and dust. Sometimes maybe even black holes can get ejected from a galaxy during one of these collisions, and they just kind of hang around in something called the circumgalactic halo, which is this big puffy region around a galaxy full of all the stuff that's been ejected. And it is actually the circumgalactic halo of a galaxy that makes first contact during a merger. So in about 4.5 billion years, the Milky Way and Andromeda galaxies will collide, but by some estimates, our circumgalactic halos are already touching. Oh, I talked about this in...
Moiya's so giddy.
You can't see it, but I really, really am. I talked about this in my Milky Way book, and the Milky Way, who is super in love with Andromeda, says that it's like, that first moment right before your fingers touch.
Oh,
it's
yes, that's such an exciting moment.
Yeah, it's so like back in the Regency period where like a single finger touching was like so sexually charged. Like that is how the Milky Way feels right now with Andromeda. But it's not like that's going to be the first merger that the Milky Way experiences. Most galaxies grow through small mergers, so we know that the Milky Way didn't just form at its current size.
Right.
It accreted and gathered material over time through these mergers. I feel like I may have skipped over a piece of information about how common these mergers are, and I did. Looking back in my notes, I missed one sentence. I found a paper. Well, I was looking for the average galaxy merger rate, and I found one paper that said that massive galaxies, on average, will have 3 major mergers in their lifetime. So the Milky Way has had several mergers, but most of them have been minor, with small satellites or little dwarf galaxies that got absorbed. But the cool thing about even those minor mergers is that they leave behind a remnant. So astronomers can look at different parts of the Milky Way galaxy and piece out its merger history. Those astronomers are called galactic archaeologists.
Love that. Great name.
I know, right? Great name. One of my advisors in grad school was a galactic archaeologist, and I got to do a galactic archaeology project with him. His name is Keith Hawkins. He's now a professor at UT Austin. But it's really cool how they use information about the chemistry and the motion of stars to figure out where these groups of stars came from. A lot of the remnants that are left behind are what we call globular clusters. These are like little kind of spherical collections of stars. A lot of them are out in the Milky Way's halo, but some of them are in the disk and moving around. We also see these remnants as streams of stars, so not like spherical clumps, but drawn out streams. And we can study their chemistry and their motion to figure out if they originated in the Milky Way or outside of it, because the Milky Way has kind of like a chemical fingerprint. We know what the Milky Way's composition is, and it's different from other galaxies, even other galaxies in our neighborhood. So we actually can tease out these differences. The Gaia satellite has been really helpful with this because it gave us precise positions and motions for 1 billion stars in the Milky Way, and that let us study these different remnants of old mergers.
Hey friends, it's Moiya here. Corinne went to get a closer look at one of the cars she wants to claim, so I figured now would be a good time to thank our patrons who support the show financially every single month. We really appreciate you all so much, but we want to extend a special thank you to our sun-like stars, Lissa, Scott Reynolds, Ian O'Leary, Augustin, and Tom T. Thank you, and please stay golden. If you aren't already one of our patrons, then you can join this amazing group of people. You can hear your name on the podcast and even make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. Each episode, I put together a list of resources, some research notes that I use to put together the episode, and I share them with our patrons. And we're also offering annual memberships, where if you sign up for a year up front, you end up with a 13% discount across the entire year. That's 1% for every constellation along the sun's ecliptic path. You can find our star chart, our Patreon info, and more at our website, palebluepod.com, or you can go right to the source. Go right to patreon.com/palebluepod if you already know you want to support us financially. And if that's not possible for you right now, that's totally fine. You're still space, and we love you guys so much. There are other ways that you can support our show. You can rate and review us on whatever podcast app you use. I really enjoy reading them, so please leave us a little note there if you can. You can also share the show with other people. Like, take a link to an episode and send it to a friend who you think would enjoy it. That's a great way to help us grow, and we would really appreciate it. Before we get back to the episode, I do have a podcast recommendation for you. It's another show in the Multitude Collective, and it is Big Game Hunger. This is a weekly comedy show where Jenna Stieber and friends craft the next big video game every single episode. They start with a randomly generated genre, concept, and vibe with kind of rolled dice type of apparatus. And Jenna, with a variety of funny and game-obsessed guests, will take those randomly generated ideas far enough that they can pitch it to a shadowy board of rich investors. By the end of the episode, they will have honed an IP so irresistible that you will surely be ready to risk $25 for it on Steam. Unfortunately, they're never actually going to make their release date, but you can still laugh about games you love and learn about game trends from Big Game Hunger. New episodes come out every Monday, just like Pale Blue Pod. So make Mondays a big podcasting day. Listen to Big Game Hunger wherever you get your podcasts. All right, Corinne is back. It seems she has made her decision. She knows what car she's going for when we finally get the chance to ride. So let's get back to this episode.
So with Gaia data, different astronomers have been able to figure out that the Milky Way has had 6 or 7 significant mergers in its past. Not all major, but significant. So one of them was the Sagittarius merger. We know about this from a few different clusters of stars, but also something called the Sagittarius stream. And I studied the Sagittarius stream in grad school, picking out its range of chemical properties. And this is a relatively larger merger that we can still see the effects of. There's something called the Cetus merger, something called the Arjuna merger, one called the LMS-1 merger. All of these mergers that I'm listing now are coming from a paper by Malhan et al., 2022 in the Astrophysical Journal. And then this paper put forth a claim of a new, actually really old merger, one that would have happened early on in the Milky Way's history, and it was the Pontus merger, with a very small satellite galaxy of the Milky Way. And they can tell that it happened a long time ago, and it was a small galaxy because the ripple effects that they're seeing from the merger are so washed out by now that it gives that information. And then my favorite merger in the Milky Way's history. Yes, I am the type of nerd who has a favorite merger in the Milky Way's history. Is the Gaia-Enceladus merger. This happened about 8 billion years ago, and it was a pretty major merger. The mass ratio was about 4-1, so this Gaia-Enceladus was a smaller galaxy in the local group, a quarter to a third the size of the Milky Way. And it left the Milky Way with a very noticeable remnant, which astronomers call the Gaia sausage.
Love it. Love sausages.
Love it. No notes, right?
Perfect.
Another
perfect thing.
The Milky Way in my book also commented on that and how it was a suitably disrespectful name for this interloper that it had to best in battle. I will say that I'm gonna read an excerpt from my book later in this episode, and throughout the book I talk about galaxy mergers as interpersonal interactions between galaxies, and so some of them are violent, like the Milky Way fighting Gaia-Enceladus, but some of them are romantic, like the Milky Way eventually merging with Andromeda, who it loves, and that's compared to more like a marriage. So I love the Gaia-Enceladus merger. And then I also found a paper from this year, a fresh paper by Donlan et al., May 2024, in the monthly notices of the Royal Astronomical Society. And they claim that they have evidence suggesting a much more recent merger, even more recent than Gaia-Enceladus, and it would have happened about 3 billion years ago. And they call it the Virgo radial merger, saying that its ripple effects are still very noticeable in the Milky Way galaxy. But it's very new, so people haven't had the chance to comment on it or push back. So take that with a grain of salt. And if I see something that changes this outcome, I'll give a little update later on. That was the past merger history, but the Milky Way is going to continue experiencing mergers. Even now, as we speak, it is actively drawing in material from the Large and Small Magellanic Clouds, these two little satellite galaxies that orbit really close to the Milky Way. So we are right now merging, but we are on our way to an even bigger collision. We are expected to merge with Andromeda in about 4.5 billion years. At least that's when it's going to start. But the whole process can take like up to 6 billion years. Right now, Andromeda is 2.5 million light years away from us. And even when we were first studying it, like back in the 1920s when we first learned about galaxies being a thing, we could tell that Andromeda was different from a lot of other galaxies we could see because it was blue shifted, meaning it was moving towards us instead of away from us. But it wasn't until 2012, that we realized that it's actually coming right towards us, like it's on a collision course.
That's so recent.
So recent. I was shocked. I really was. I thought we knew about this a lot earlier. But it wasn't until 2012 that we had enough collected data from the Hubble Space Telescope. It collected data from 2002 to 2010, and it gave us a more precise vector for Andromeda's motion and told us that, it is actually on a collision course. And then we were able to calculate about how long it's going to take. That paper that, as far as I can tell, was the first one showing definitive, quantifiable evidence that the Milky Way and Andromeda are going to collide. It was published by van der Merel et al. In the Astrophysical Journal in 2012, and it only has 79 citations. I feel like it should have a lot more citations than that. This is the paper that told us Milkomeda is going to happen, and it has fewer than 100 citations. Oh yeah, astronomers love to give couple names to these galaxies.
I am completely on board with, as we should.
So yes, Milkomeda. We learned about it in 2012, and this paper is, in my opinion, criminally undercited.
You hear that, everyone?
Go cite it.
You have to go cite this.
You have to. It's an assignment from us. According to simulations about this merger, there's a roughly 50% chance that our solar system will get pushed further out towards the edge of the Milky Way galaxy during the initial pass. But there's about a 12% chance that our solar system gets flung out of the galaxy entirely.
Whoa, see ya.
Ooh, see ya. But, it honestly doesn't matter because by then the sun will have puffed up into its red giant phase. Mm-hmm. The Earth probably isn't going to be around anyway. So who cares if our solar system gets flung out of the galaxy?
No big deal.
No big deal. The sun it's moved on to the next phase of its life anyway. But yeah, that's going to happen. 4.5 billion years. The Milky Way and Andromeda are going to get married, as I like to say in my book. I don't know how long astronomers have actively been studying galaxy mergers. I'd guess probably not that long. Probably the 60s when we had telescopes that were going and looking at different examples of merging galaxies. But there are a few different ways that we can study galaxy mergers. We can study them through observation or through simulations. Observation is great because it's direct data. It tells you statistical properties that actually exist out in the universe, but it's tricky because it depends on you first identifying that these galaxies are merging in the first place. And you can do that by eye, or you can do that with a computer algorithm, perhaps artificial intelligence, but it doesn't have to be. Mm-hmm. I don't know if you remember from our AAS episode, I talked to a few people at AAS, the American Astronomical Society conference, and they were doing galaxy merger projects. One of them was one of my mentees, Emma Kleiner. She's using a combination of eyes and algorithms. She's turning a bunch of people's eyes into an algorithm using citizen science, and she's using the public's help to distinguish single star-bursting galaxies that look very bright because they are forming new stars from pairs of merging galaxies that look bright because they are actually two galaxies instead of one. So that's just one example of how we can first identify galaxy mergers and then from there go on to study their properties. How is their star formation rate being affected? How is the gas being moved versus the dust versus the stars, for example. There are so many questions that we can try and answer in a galaxy merger.
Cool.
I have a few notable galaxy mergers for you, things that have taught us new stuff or just been weird, made us go, I didn't know that could work that way out in space. One of them is WAS 49. It was discovered in 2017. It's these two galaxies that are merging. One of them is relatively large and kind of disky, although not perfectly spiral, I don't think. And then the other is a dwarf galaxy that has a little surprise in it. This dwarf galaxy has a black hole in its center that is more than 2% of its total mass, which is a huge fraction for a dwarf galaxy. Even more surprising, the black hole is active. It is an active galactic nucleus, meaning it's so energetic, it's so massive and so energetic that it's sending out those light streams.
That's a surprise.
It's
right.
a surprise.
That
we
is
don't
the
know
surprise
why.
at the center.
Like, why is it happening in this tiny little galaxy? We don't know.
Isn't there a candy or something that has a surprise at the center?
Like the Tootsie, huh?
Tootsie Pop. Yes.
Yeah.
Well, how many licks does it take to get to the center of that galaxy?
Oh, I want to see that commercial. I want to see the owl doing that.
Desperately trying.
So that's just one weird example of a galaxy merger. Another is Stephen's Quintet. Have you heard of Stephen's Quintet?
I feel like maybe you've mentioned it to me, but I don't remember what it is, and maybe we've never talked about it.
Either way, it is kind of a famous little cluster of galaxies. It was discovered in 1877 by a French astronomer, Edouard Stephan, and it was the first compact galaxy group to ever be discovered. Usually groups of galaxies are further spread apart, and there are a lot of galaxies in them. Our galaxy group, for example, has like 50 galaxies in it. This is a compact galaxy group, meaning they're really close together, and there are only 4 of them, which is confusing because it's called Stephen's Quintet, right? So we saw this in 1877. There were 5 galaxies, all very smushed together. Over time, as we got better at calculating the distances to galaxies, we learned that Stephen's Quintet is actually 4 galaxies that are very close to each other, but that cluster is about 290 million light years away from us. And then in the foreground, about 40 million light years away from us, is that 5th galaxy that is just a lot smaller, but it's closer, so it looks like the same size.
Oh, okay.
Yeah, it's just a trick of the eyes. But those 4 galaxies, they are very close to each other, and they are interacting. 2 of them have even started to smush together and actively collide. Galaxy clusters can also collide, not just individual galaxies. There's a really famous example of this with the Bullet cluster. The Bullet cluster, it's like 2 clusters of galaxies that have passed by each other. They're about 3.8 billion light years away, so pretty far. And they were discovered in 1998. But in 2006, when people looked at the different pieces of the Bullet cluster, like looking at the stars versus the gas and dust versus just all of the mass that they could discern. In 2006, they saw that the mass from stars is in a very different location physically from most of the mass in the Bullet cluster. And so what they found was kind of irrefutable evidence, some of the first irrefutable observed evidence of dark matter in galaxies.
Ooh,
because
fun.
That place where there was a bunch of mass, but there weren't any stars or dust or gas, that's dark matter. And it didn't just show them that dark matter existed, but it also showed them how dark matter behaves differently from other types of matter, because the dark matter blobs are physically in a different location from the star blobs. It's easier if you look up a picture of the Bullet cluster, and you can see that usually in the pictures, there's pink and blue parts, and the pink is where all of the stars are, and the blue is where all of the dark matter is. And you can see that it's separate.
Yeah, you can see it.
It's nice. It's nice to watch. Okay, so I said we could study galaxy mergers through observations, but also simulations. And there are a bunch of different simulator packages that already exist to simulate galaxy evolution and galaxy mergers, but I have a couple here that I want to specifically talk about. One of them is called Illustris. This was a huge universe simulation that was finished in 2013, but it ran for years on really powerful computers, taking into account a bunch of different physical processes. So I have here a quote from the Illustris page. It says that it took into account, quote, gravity and hydrodynamics, very complex physical processes such as chemical processes in the diffuse gas, radiation, and medical fields, which also affect cosmic structure formation, and physical processes such as star formation-driven galactic winds and black hole thermal energy injection are modeled throughout cosmic history. That's a lot. That's a lot of words. It's a lot of words saying what they're covering. But it's everything. They're looking at chemical evolution. They're looking at differences between gas and stars. They're including processes of radiation feedback and wind and pressure feedback into the system. Like, they're taking all of this stuff into account and creating a really, I'd say, accurate simulation of how galaxies form and evolve over time. Maybe in the future we can do more of like an Illustris or like one of those big simulator project. We can do a whole episode about that. But Illustris has been able to simulate galaxy mergers and tell us what to expect, and then we can compare the simulation to observations, which is useful. Another simulation code that I have heard about and seen good results from is the FIRE simulation. This stands for Feedback in Realistic Environments. It's a straight acronym, and I love it.
I know, that's so rare here.
Truly. And similar to Illustris, it takes into account a bunch of different physical processes, but this one is really trying to pay attention to small scale processes, like processes that you wouldn't be able to see in a telescope because it happens on such a small scale. So they're looking for the energy, momentum, mass, and metals that are returned from stars back into the system as the stars evolve. They're also directly following the predictions of stellar population synthesis models. So they're taking into account how new stars form and then go about their evolutionary phases. Illustris doesn't do that. It focuses on like bigger scale things. And it's important to have simulations that focus on these different scales so you can work out different details and iterate over time.
Sure, yeah, that makes sense.
Yeah. Any questions about galaxy mergers or how they work or how we study them before we move on?
I think I like how common, or not how common, but how they're much more frequent than I thought.
Yay.
I mean, I guessed right. But I think in my head I still was like, oh, that's like a end of life stage thing that doesn't happen all the time. So that I like that. Yeah,
they are already happening. So we don't really have to be afraid of what would happen if a collision occurred, because like collisions are already occurring. So what's happening now is what would happen if collisions occurred.
Love it.
And like some parts of what's happening now suck. Sure. But a lot of what's happening now is great.
Yeah.
The next thing I wanted to do, I thought it'd be fun to read some excerpts from the Milky Way, specifically the chapter, which is my favorite chapter to write, called Crush, where the Milky Way is talking about not just the crush that it has on Andromeda, but also the way they're going to crush together in the future. And then I thought maybe we could plan their wedding.
Let's do it.
Okay, great. I just have a few paragraphs that I wanted to read, so you can get a sense for their romance and what they've been through in their relationship.
What kind of wedding they want.
Yeah, exactly. This is from the Milky Way's perspective, just so you know. From our first shared glance 10 billion years ago, I could tell that Andromeda was special, despite being much smaller and dimmer. I wouldn't say I have a type when it comes to galaxies. Spirals and ellipticals are all beautiful in their own ways, and bars add some nice chaotic structure. But I have always found it hard to resist a galaxy with some mass to it. That's mass with an M. Nor was it only the impressive dark matter halo that Andromeda had already managed to collect, though I'd be lying if I said I wasn't intrigued by such a sure sign that this galaxy would one day be a mighty force to be reckoned with. It was more than just Andromeda's physical appearance that caught my attention. I was pulled in by the way Andromeda moved through the group with a vigor and confidence that seemed to say, yes, I'm here, and I want you all to know it, but I don't care what you do with that information because I don't need any of you. It was a self-possessiveness that seemed to have its own gravitational force. I adored how Andromeda fed so unself-consciously and without reservation on other galaxies. To this day, when Andromeda overpowers a smaller galaxy, it doesn't seem violent. If anything, it leaves the impression that other galaxies just offer themselves up to Andromeda. Please, take everything that I am, for I am unworthy to exist in your presence. Pathetic, but relatable. I knew I had to do something to pique Andromeda's interest, so I picked a fight with the most colossal opponent I could find. Weighing in at 50 billion solar masses, Gaia Enceladus was one of the largest dwarf galaxies in the neighborhood and wanted everyone to know it. Gaia Enceladus sauntered around the local group, threatening to fight and eat everyone in its path, insulting their velocity dispersions, and greatly exaggerating its gravitational influence. It had to be stopped, and I was the best galaxy for the job. My hopeful but not desperate ploy for attention worked. I heard from Sammy, which is the small Magellanic Cloud, who claimed to have heard from Fornax by way of Phoenix, then Pisces, all the way back to Pegasus, that Andromeda was impressed by how I had handled my encounter with Gaia Enceladus, and was interested in getting to know the galaxy who had rid the neighborhood of such an irredeemable bully. Knowing Andromeda was open to my advances, it was time to make my move, but after watching galaxies throw themselves at Andromeda for too long, I couldn't rush into anything. The fruits of romance are far sweeter if given plenty of time to ripen, so I sent Andromeda a message the old-fashioned way, with stars, of course. And then the Milky Way goes on to say how it used hypervelocity stars, which are these stars moving so fast they overcome the gravitational influence of the galaxy, so they actually get flung out of the Milky Way. It says that it's using these as love notes to send to Andromeda.
I love that.
I love it so much.
Like flowers.
Like flowers, yes. So the rest of the chapter also talks about Andromeda's past mergers, which are past relationships. And the Milky Way says that, like, yeah, of course it's jealous because jealousy is like a natural emotion.
Yeah.
But it doesn't resent Andromeda. And it would never want Andromeda to, like, deny itself pleasure or food or, like, entertainment just because the Milky Way loved it. Like, that's not fair. So, yeah.
Love that.
Yeah. This is the chapter in the book that made Neil deGrasse Tyson call me kinky for how I describe galaxy mergers.
I'm picking up on that. I get it. I see how we got there.
Because I was like, yeah, it's cannibalism. The galaxies are eating each other, but also it's romance.
It's way more fun to think of it like love than it is cannibalism.
Yeah. And
Love
I think it can be both. It's very complicated, these interpersonal dynamics between the galaxies. But now that you know a bit more about the love story between Andromeda and the Milky Way, I'd like to plan their wedding. I think maybe starting with like a theme. Ooh. Do we think there'd be a theme?
That's a great question. Because what's coming to mind to me is the invitation, which is like those layered invites where it's like there might be a textured or like thick back and then like a brad clip at the top with a vinyl top. So all the info's on this like kind of clear piece of paper. So what if it was two of those pieces, kind of clear pieces of paper with bits of info, and when they overlap, like they've merged, you can read all the info.
Corinne, that's beautiful.
And that's the theme. The theme is their love.
The theme is their love. The theme, it's stars. What if they have all of their stars that are their little love notes, like strung above, like fairy lights. Like that's illuminating the
it's
ceremony.
A fairy light, exactly.
Amazing.
That's the kind of wedding.
Amazing. So star-themed decor.
Yeah. Yes.
Do you think band or DJ?
Ooh, I think band.
Yeah? Okay.
A good one.
A good band. Well, yeah, they can buy the best band.
Of course.
Around.
So then absolutely.
Right. I don't know what else goes into you've had a wedding.
Champagne kind of drink.
Okay.
My wedding was so non-traditional that I imagine theirs would be too, despite being older than the tradition itself.
Yeah. What weird little wedding traditions do we think they would have?
Well, Eli and I walked down the aisle together, and I feel like they would too.
Oh, I love that. I wanted to do that. That's nice.
It's a fun thing to do. I think also, you get so nervous right before your wedding. It's really nice that your person's there with you.
Yeah.
So I feel like the Galaxies would do that. They would invite perhaps neighboring galaxies to attend. Mm-hmm. As long as nobody merges that night.
Right. Like, don't steal their thunder.
No.
Yeah. I think the Milky Way, at least, is very attached to its stars. Mm-hmm. So I think they would be in attendance.
Yes.
Perhaps some of the, like a little ring bearer.
Oh, how
and, like,
cute.
a little flower star.
Love that.
I feel like the Milky Way wants to write its own vows.
Yes.
But I feel like Andromeda just like wants the whole ceremony to be done.
Yeah,
it's just like,
that's
I love you,
exactly
but
what
like
I
I don't
feel.
need to do all this.
Yeah, it's like, why would I need to do that? You know I love you.
Yeah. So I think they do write their own vows, and the Milky Ways is like so
Waxing
loving
poetic.
and like
Yes.
exactly like makes everyone cry.
Yeah.
And then Andromeda's just like,
Okay, well,
I love you, and we're gonna keep doing what we've been doing for the
Yes.
last several billion years.
so see you later. Yeah, exactly.
Nice.
That's, I guess, the food.
Well, their food would be other galaxies. Their food.
Oh, you're
their
so
food
right.
would be the remains of their enemies.
You're so right. I when you're so excited about the couple, I feel like all of the details of the wedding don't matter at all. Mm-hmm. And I feel like this is one of those couples where it's like they're outshining any kind of event experience. That just being in their presence makes it the best wedding.
You're right. It's gonna be a star-studded wedding, no matter what, by definition.
Absolutely.
And I think that the big group dance that they do during the reception is going to be the wobble. All of the stars are going to do the wobble.
Love
and
it.
then all of the astronomers who study radial velocities are going to get very confused.
Yes, it will be a very confusing day for science, but ultimately a night to remember.
I hope that our invitations with the two pieces of paper that come together to create the message, I hope that they are in the intergalactic mail as we speak.
Yeah, I'm sure they are. Well, it's going to get here any day now.
It must. But that said, I do believe we are up next.
Oh my God, I can't
It's
wait
almost
to
our
bump
time
in.
for the bumper cars.
Okay, don't bump into me. I'm just going to try to floor it around the track.
Cool. You're just going to be running your own race. I am going to see how close I can get to someone without bumping them.
That's a good challenge.
Thank you.
Okay, listeners, wherever you're bumping today, remember you are space.
Sure are. Bye. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.